to be doing partial differential equations like we've been doing so far, but now in higher order dimensions, right? Um, the idea being that we've been mostly focusing on one-dimensional rods and one-dimensional waves, but now we're going to look at how you can solve partial differential equations in 2D, 3D, etc., right? So we're going to use the example of the wave equation as a way to show how to solve these kind of problems. So I'm going to just write out the wave equation, but this time in its multivariable form. That is, the gradient squared, partial squared u partial t squared is equal to the Laplacian squared of u, which if you're not familiar with Laplacian is, it's the dot product of the gradient. It's the gradient dotted with itself for a function, or in other words, the divergence of the gradient. So without that vocab, a better way to think about it is in one dimension, the Laplacian looks like this, and in in 2 dimensions, it looks like this. Hold up. And in 3 dimensions, you could expect a z and so forth, right? So we're going to use this to solve the vibrating membrane problem, which is, we've dealt with a vibrating string before, right? And the wave that it forms. But now what if we had a membrane, right? A 2-dimensional wave that went back and forth, that wave back and forth. So what that partial differential equation would look like now is partial squared u partial t squared is equal to partial squared u over partial x squared plus partial squared u over partial y squared. And I should also, there is a constant, of course, forgot the constant. So just put that here. Now, how to approach this kind of problem? Well, it's actually quite similar. We use separation of variables in Fourier series, but we kind of just do them in a loop. What I mean by that is we'll separate it into two functions multiplied together. We'll say phi of x comma y, which is still a multivariable function, and h of t times h of t, right? So then we can rewrite this partial differential equation now as as phi times the second derivative of h with respect to time, and that equals k times h times still the partial derivative of phi with respect to x, or the second partial derivative, and the second partial derivative of phi with respect to y. Now, if we do separation of variables like we've done, we get 1 over k h d squared h over dh squared h over dt squared is equal to 1 over phi times partial squared phi over partial x squared plus partial squared phi over partial y squared. And this is equal to some arbitrary constant lambda. Now, we have one of our, what will be a system of 3 differential equations, and we have one of the ordinary differential equations down. Now we're going to do separation of variables again. This time we're going to say phi is equal to f of x times some g of y. So our partial differential equation here would now become g times the second derivative of f with respect to x plus f times the second derivative with respect to g times y. And this equals and this equals minus lambda times f times g. Great. Because phi is f times g, and we move the phi to the other side. So now we'll do separation of variables again. So we'll rewrite, here, wait, hold up. We'll take this, and we sum it with this term. We bring this term to the other side. And plus f of d squared g over dy squared equals 0. Now let's pull the g's out. Or, I guess it doesn't matter. We'll pull the g's out. So we pull the g, giving us d squared f over dx squared plus lambda f plus f times d squared g over dy squared equals 0, or we can move this to the other side, making it, we can say equal minus f times d squared g over dy squared. Then we divide both sides by d, divide both sides by f, and we get 1 over f d squared f over dx squared plus lambda f is equal to minus 1 over g d squared g over dy squared equals some function, call it some constant now, call it mu, or mu. Great. Now what we're going to do is we have this. Now what we're going to do, and I should, here, let me, to make the simplification easier, we're going to move the minus sign to this other equation. You'll see why in a minute. But, oops. Move this minus sign here. But let's, in fact, actually, let's move it inside here. And you'll see why. It'll make things easier. But now we can do separate. Now we have our other two differential equations, which is d squared g over dy squared equals minus mu g and minus d squared f over dx squared minus lambda f, now plus mu of f equals 0. Move the d squared f over dx squared to the other side and pull out the f, or f, leaving us with minus lambda minus mu times f equals d squared f over dx squared. And so now we have a system of 3 ordinary differential equations. 1, 2, and 3, all in very similar forms. Here, let me rewrite this last one real quick. KH, all in very similar forms. And now we just have to solve for lambda and mu using boundary conditions we're familiar with. Which, now that we have our partial differential equations separated, let's establish boundary conditions. So it's challenging to do these kind of problems for just a generic shape, which is why I picked the Cartesian coordinates, so that we can figure out what it is for if our boundary condition is in the shape of a rectangle. So in this case, if we had a boundary in the shape of a rectangle, we'd have 4 different boundary conditions, and I'll write them out. We'll have u u at hold up. Okay, there we go. Sorry. We'll have u at, we'll label these as 0 through L and 0 through H. And so we'll have u of 0, comma, we'll keep the boundary conditions simple, but you realize that like no matter what the boundary conditions are, it's pretty transferable. We'll say, but we'll just keep them all to prescribe boundary conditions of 0. So 0, comma, H, comma, T equals 0. And then u of 0, L, comma, 0, comma, T equals 0. And then finally, u at, wait. Let me rewrite these boundary conditions real quick. Sorry, u at 0, comma, we'll say u at x, comma, 0, we'll say. That's how you're supposed to do it. Sorry. So for this boundary here at x, comma, 0 is all equal to 0. And then similarly here, it would be x, comma, h, so then up on this boundary, and L, comma, y, and 0, comma, y, comma, t equals 0. Great. And what you'll realize is due to our separation of variables, we can actually rewrite this now as g of 0 equals 0, g of h, right, equals 0, and then f of 0 equals 0, and f of L equals 0. So now that we have our boundary conditions and separated our variables, what we can do is we can just use what we know about like Sturm-Liouville problems and boundary conditions and how they work with eigenvalues and eigenfunctions, and we can just solve this equation. So we'll notice that our boundary conditions are these prescribed ones, which means our eigenfunction is this, our lambda value is this, and our series will look like this. So what we're going to do is we're going to take each of our differential equations, and we're just going to write, we'll label them. So this mu is equal to n pi over L squared, n pi over L over L whole squared, and the associated function is sine of n pi over Lx. Similarly, down here, we can say that lambda minus mu is equal to, we'll call it a different variable, m pi over L. M pi over, oh wait, and sorry, this should not be L, this should be H, because as you'll know, G is with the function y, so then the boundary condition would be H. And similarly here, it's be m pi over L, and we know what mu is now, so we know what lambda is as well. Lambda is a function of both n and m, and it's m pi over L squared, whole squared, plus n pi over H whole squared. Okay, great. And the solution to this would also be sine of m pi over L times x. And then up here, the solution to this would look like would also be a sine function, sine of this time. Let me think. It'd be sine of one sec. N pi over L squared T square root of k with eigenfunction with an eigenvalue of lambda, which we just solved for below. So now we can put together our entire general solution to our partial differential equation, which is that u of x comma y comma t is equal to the sum from n equals 1 to infinity of sine of, and sorry, this is not n pi over L. Sorry, I miswrote that. It would be, wait, sorry. The solution to this would be, not this, sorry. It'd be sine of because because it doesn't have boundary conditions, it just has the initial condition. But what we can say is it'll be sine of t root lambda root k. Or sorry, not root k, just k. K, we'll say kt times root lambda. Great. And we know what lambda is now. We solved for it below. But anyways, we'll write up our whole solution. So we'll say it's the sum from n equals 1 to n equals 1 to infinity of some constant a sub n. And we'll see it's a sub the sum from n equals 1 to infinity of the sum from m equals 1 to infinity, because we have that other eigenvalue, of some constant a sub nm times, and let me fix this, it'd be kt root lambda a sub n sine of n pi over h y times cosine, or sorry, sine of m pi over lx times sine of kt root lambda. Great. So now, with this, what we can do is, okay, so I didn't establish it before, but initial conditions will just be pretty basic. We'll just say u at x comma y comma 0 is equal to some alpha x comma y. And because it's the second derivative with respect to time, we'll need a second boundary initial condition. So we'll say u prime at x comma y comma 0 is equal to beta x comma y, some function. Great. So using this, we can now take our differential equation, our solution to our partial differential equation down here, and we can solve for the constant, figure out what the constant here is. So first, plugging in t equals 0, we get sine of 0 equals 0. Or wait, sorry. Sorry, wait, I think I messed this up. This should be sine of kt root lambda times cosine of kt root lambda, right? Because we don't have any boundary conditions that, or initial conditions that would disagree with that. So that means we'll have two terms here, right? Plus this time cosine of kt root lambda. So now, with this fully formed partial solution to our partial differential equation, we can figure out what our two constants are, a and b. I'll call this b. And we do that by plugging in 0 here. So then this term will cancel out. This term will stay. We'll get alpha of x comma y equals this function. And we can use the methods that we've developed to figure out what our constant b sub nm is. So what you'll notice is that if we hold y constant, then the only thing that changes is m. And so, one second, let me rewrite this so that it makes more sense. But what that means is that this is just equal to, looking at our integral table here, 2 over L. It would be in the form of this. So we could say that the sum from n equals 1 to infinity of b sub n m of sine of n pi over h y is equal to 2 over L, the integral from 0 through L of of alpha of x comma y times sine of n pi over L x. M pi over L x. And then we can do that again. So this time b sub n m is equal to 2 over h times the integral from 0 through h of this function, which I'll copy, right? Because this is almost like our initial condition now for this infinite series, times dx right here, dx, times this time sine of n pi over hy dy. And we can simplify this a little to get what our coefficient is. B sub nm is equal to 4 over h L integral from 0 through h times the integral from 0 through L of alpha x comma y sine of m pi over Lx sine of n pi over hy dx dy. Dx dy. And that's for b sub nm. Now, to figure out a sub nm, we have to take the derivative, right, using our second initial condition. So u prime, I'm not going to write it all out, but we know that this turns into a cosine term, and this turns into a sine term, and sine of 0 is 0, so this cancels out, leaving us with just this. So u prime would be equal to this function, or at least this part of the function, times, well, u prime at 0, which is beta, x comma y is equal to all this times k root lambda n sub n which we have, which we solve for below. Great. So now now we'll do a similar process here where we know that this portion of the equation, if we held y constant, will equal the integral, or sorry, 2 over, here, wait, put the constants in front, k root lambda sub nm would be equal to 2 over L, the integral from 0 through L of beta x comma y times sine of m pi over L x dx. And we know that, and then we can do it again, and we can move the constants to the other side so that we get a sub nm is equal to, pretty similar in form, except it's 4 over h L k root lambda times the integral, equals, here, I'll just copy paste it from here, equals this. Great. Dx dy. Great. And so that is how you do higher order PDEs. You'll see it's a very similar process. Separation of variables followed by Fourier series, looking at boundary conditions, and it's very like plug and play. So based on what your boundary conditions are, you'll have different coefficients and eigenfunctions and eigenvalues. But that's how you solve it. This is just one example, but you can see how this is clearly easy to do for other functions, other boundary conditions, and also other equations like the heat equation instead, with slight differences. So hopefully that gave you a good introduction to it. Next video we'll be looking at now how to do it in polar coordinates and introducing like the Bessel function, and we'll talk about that later. Thank you.